Next up, we're going to discuss oxidation-reduction reactions, also known as redox reactions. So redox reactions are reactions in which electrons transfer from one reactant to another. So in these types of reactions, one of the reactants is losing electrons, the other one is gaining electrons. And sometimes it's a little bit difficult to kind of like keep them straight, like which one is which. So I've got this handy chart for you. So when we have a reactant that loses electrons, we say that that reaction is oxidized. Those electrons that the oxidized reactant loses go over to the other reactant, causing the other reactant to gain electrons and be reduced. So one of the reactants is losing electrons, one of them is gaining electrons. So the one that loses electrons is becoming less negative, and that's because electrons are negatively charged particles. When you're losing them, you're getting rid of some of your negative charge. The one that's gaining the electrons is becoming more negative. So the one that is losing its electrons is causing the other reactant to be reduced because it's causing the other reactant to gain electrons, so it's called the reducing agent. Whereas the one that's gaining the electrons is called the oxidizing agent because it is causing the other reactant to be oxidized. In order to keep them straight, which one is which, an easy mnemonic to remember is oil rig. And that stands for oxidation is losing electrons, and reduction is gaining electrons. So that's kind of like an overview of the definitions between oxidation and reduction. So what does that even mean? In order to talk about that, we need to talk about oxidation states, also known as oxidation numbers. And this is basically a method of counting electrons. And so you can count up the electrons using oxidation states of the reactants and then determine the oxidation states of the products. See which ones are changing, so that way you can figure out what is losing electrons and what is gaining electrons. So first we're going to talk about the rules of oxidation states. This is how you assign oxidation states to an atom. So basically how you figure out what the oxidation state of an atom is. And these rules have to be followed in order, or else you have a chance of not getting the correct answer. So the first rule, the oxidation state of an atom in a free element is 0. So what does that mean? Well, an atom in a free element is something like, for example, solid zinc, Cl2 gas. So remember, chlorine is a diatomic element. Neon gas. So these are all elements that are pure in their most stable form. And so all of these would have an oxidation state of 0. Rule number 2 is the oxidation state of a monoatomic ion equals its charge. So a monoatomic ion, mono meaning one, atomic meaning atom. So ions that contain one atom have an oxidation state equal to the charge. So that would be like Cu2 plus would have an oxidation state of positive 2. So side note, we usually write charges with the number and then the charge. Oxidation states, we usually write the charge and then the number. It doesn't really matter all that much. If you forget, I'm not going to mark one or the other one wrong. But that's just kind of the kind of like the accepted way of writing these. So another example of a monoatomic ion would be Cl minus, and that would have an oxidation state of -1. Na plus would have an oxidation state of +1, and so on. Rule number 3. The sum of all oxidation states in a molecule is equal to the charge on that molecule. So I'm actually going to come back to this one in a few minutes because this one is easier to figure out in the context of a whole example where you're looking at all of the rules at once. So rule number 4. In compounds, metals have positive oxidation states. So if we have an ionic compound, NaCl, our Na is going to have a positive oxidation state, so a +1 oxidation state. Our Cl, in order to balance out that +1, will have a 1 minus or a -1 oxidation state. So as you can see, for ionic compounds, they work really similarly to charge. It's not exactly the same thing. Oxidation states are just a method of electron counting, but in some cases, it ends up being the same number. So calcium is group 2. It's going to have a +2 oxidation state. Each fluorine atom is going to have a 1 minus oxidation state because there are 2 of them. And those 1 minuses combined will balance out the 2 plus. So again, works really similarly to charge even though it's not exactly the same thing. So an example of how we can really tell, like, it's not the same thing. Nonmetals also have oxidation states even if they don't have a charge. So again, we have to follow these in order. Hydrogen usually has a +1 oxidation state, oxygen -2, group 7A -1, 6A -2, 5A -3. And that is regardless of whether or not whether or not it's an ionic compound. So whether or not those particles are charged, it doesn't matter. Whether or not they're charged, they will still have some oxidation state. So there's all the rules. Here's how you actually use them. So basically, we kind of go through the checklist step by step until we assign all of the oxidation states. So for A, we have chlorine. Well, first we go to rule number 1. The oxidation state of an atom in a free element is 0. Is this a free element? Yes, it actually is, and it's actually one of the examples that I just showed. So because that is a free element, then that is going to, each chlorine is going to have an oxidation state of 0. So oxidation state is going to equal 0 for each chlorine. The key here is that every atom has its own oxidation state. We're never going to have an oxidation state for an entire compound. You have to go atom by atom. Okay, so for B, Na+. The oxidation state of an atom in a free element is 0. Well, we don't have Na in its free element. Na in a free element would be just sodium metal. Instead, we have ionic sodium, so Na+. Rule number 2, the oxidation state of a monoatomic ion equals its charge. That is what we have in this case. So, and again, this is an example that I just showed. Na+, the oxidation state is going to be a +1. So, oxidation state equals +1. Okay, so now we have 2 different atoms in this compound. We have K and we have an F. So we need to identify those oxidation states individually. So again, we go up to our rules. Rule number 1 does not apply because it's not a free element. Rule number 2 does not apply because it's not a monoatomic ion. Rule number 3, the sum of all oxidation states in a molecule is equal to the charge on that molecule. That's something we can use. So the charge, or the oxidation state of K So I'm just going to abbreviate that as K, plus the oxidation state of F is going to equal to 0, because that's rule number 3. It has to equal to the charge on the overall molecule. This is a neutral molecule, so the sum of the oxidation states has to equal 0. But we still don't know each atom, so we have to figure that out. In compounds, metals have positive oxidation states. So potassium is a metal, and it's a group 1 metal, so we're going to use the fact that it is a group 1 metal, and that is going to give us its oxidation state of +1. And since we know that these have to equal 0, we know that the oxidation state of F has to equal -1. And that is also consistent with these rules over here, the group 7A. Fluorine is a 7A atom, and that has an oxidation state of -1. Now we're getting more complicated. Now we have 3 atoms. So rule number 1, free element, does not apply. Rule number 2, monoatomic ion, does not apply. Rule number 3, the sum of the oxidation states has to equal the charge. That one we can work with. So we have the oxidation state of the carbon plus 2 times the oxidation state of the oxygen, because there are 2 oxygens, and each one has its own individual oxidation state. And that is going to equal 0. And I'm actually going to change my abbreviation here because it looks like 2 times 0 plus C equals 0, so I'm just going to abbreviate that as OX for oxygen. So if we go back up to rule number 4, in compounds, metals have positive oxidation states. Well, neither C nor O are metals, so that can't really help us here. So now we go to the nonmetals. So we have hydrogen is +1. There is no hydrogen in this molecule. Oxygen is -2. There is oxygen in this molecule. So we have C plus 2 times -2 equals 0. So if we simplify that, we find out that the oxidation state of C of carbon is +4. So for our oxidation states, we have carbon is going to equal +4, and oxygen is going to equal to -2. So a -2 oxidation state for each oxygen. Notice how we write them individually. We don't write -4. -4, if you wrote that on a homework or an exam problem, would be incorrect. Okay, so next one is SO4 2-. Rule number 1, is it a is it a free element? No. Rule number 2, is it a monoatomic ion? No, it is a polyatomic ion, but rule number 2 only applies to monoatomic ions. Rule number 3, the sum of all oxidation states has to equal the charge. We can work with that. So we have the oxidation state of S plus 4 times the oxidation state of oxygen, I'm going to abbreviate that OX again, is going to equal to -2 because we have this 2 minus charge here. So that was rule number 3. And rule number 4, metals have positive oxidation states. Neither of these, neither sulfur nor oxygen are metals, so we move on to rule number 5. Nonmetals, we don't have any hydrogen in SO4 2-, but we do have, again, oxygen. So we have sulfur plus 4 times -2 equals -2. So sulfur plus the oxidation state of sulfur plus -8 equals -2. So that means that the oxidation state of sulfur is going to equal +6. So for sulfur, we have +6. For each oxygen, we have -2. Again, we don't want to write -8. That would be incorrect. And then for our last example, we have K2O2. Rule number 1, is it an atom in its free element? No. Rule number 2, is it a monoatomic ion? No. Rule number 3, the sum of the oxidation states has to equal the charge. So we have 2 times the oxidation state of K plus 2 times the oxidation state of oxygen will equal 0. So then we go back up to our rules. Rule number 4 is metals have positive oxidation states. So that means that our potassium is going to come first, and that will have a positive oxidation state. And so now we have to solve for the oxidation state of our oxygens. So if we have 2 plus 2 oxygens equals 0, we can solve on both sides, so we have 2 The reason I showed this all out is because we get kind of a weird answer. The oxidation state of oxygen in this particular example is -1. So notice how that doesn't go by this rule number 5, because rules number 3 and 4 had to come first. These ones took precedence. So rule number 3 was more important because it comes first. All of the sums of the oxidation states had to equal 0. Rule number 4, the metal had to come before the nonmetal. So unfortunately, rule number 5 did not apply to this one because the other rules took precedence. So for K, we had a +1 oxidation state for each potassium, and for oxygen, we had a -1 oxidation state for each oxygen. So that's how you assign oxidation states. But remember, we were talking about redox reactions. So how does this, what does this have anything to do with a redox reaction? Well, it helps us identify whether or not a reaction is a redox reaction. And we're not going to work on balancing redox reactions now. That will come later on. Right now, I just want you to be able to identify whether or not a reaction undergoes oxidation and reduction. So what we're going to do is we're going to check to see if any of the atoms in this reaction change their oxidation numbers. So in order to do that, we have to assign oxidation numbers for every atom. So starting with this one, carbon. Carbon by itself is a free element. So rule number 1 applies. The oxidation state is going to be 0. Same thing with sulfur. Sulfur is a free element. That oxidation state will also be 0. Notice how the coefficients don't change whether or not an atom is a free element. It just means that we have more of them. Now we have to solve for CS2. So rules number 1 and 2 don't apply. We can go straight to rule number 3, which is that the oxidation state of carbon has to be added to the oxidation states of both sulfurs to equal 0. Rule number 4 only applies to metals, which we don't have. Rule number 5, we can go up here to the nonmetals. We don't have any hydrogens. We don't have any oxygens. We do not have anything from group 7A. But we do indeed have sulfur, which is from group 6A. So that means that we have a -2 oxidation state for each sulfur, which means that our oxidation state of carbon is +4, and our oxidation state of sulfur is -2 for each one. So, did these atoms change their oxidation states? Why, yes, they did. Carbon changed its oxidation state from 0 to 4. So because it went from 0 to 4, carbon became more positive. Also, if it's more positive, that means it's less negative. So carbon was oxidized sulfur went from 0 to -2. So sulfur became more negative, meaning that it was reduced.